Now I'll see how to realize the last remaining control source, which is a current controlled voltage source. Okay, and a current controlled voltage source, it has an input current II and an output voltage VO, and the output voltage VO is proportional to the input current II, and there is some proportionality constant. I'll call it Rm. Okay, and this can be thought of as the trans resistance, just like transconductance. Okay, it is the ratio of voltage to current, but not between the same two terminals. And because a current controlled voltage source realizes a trans resistance, sometimes it's called a trans resistance, or usually trans impedance amplifier. Okay. So how do we go about realizing this? We have an input current II, right? And what is it that we need to do? We have to realize this relationship using negative feedback. So that means that we can think of V0 minus IIRM, or the negative of this as the error between desired and actual outputs. Okay. So if V0 minus IIRM is greater than 0, then that means that the actual output V0 is more than the desired output IIRM. The output V0 must be pulled down. And if V0 minus IIRM is less than 0, that is, the actual output is smaller than the desired output IIRM, then the output V0 must be pushed up. And we have to realize this using a transistor. Okay, obviously when I say current controlled voltage source, I mean using a MOS transistor. Okay, so how do I pull or push the output voltage using a MOS transistor, which is really a controlled current source? It means that when V0 must be pulled down, current must be drawn from the output node, and similarly when output V0 must be pushed up, current must be pushed into the output node. Okay, so putting all these things together and knowing how the transistor behaves, we can realize our current controlled voltage source. Okay, the method we have used is exactly same as what we used for all the previous controlled sources. Okay, there is some relationship that we want to implement, and we represent it as some error which should go to 0. If the error is positive, we have to do something. If the error is negative, we have to do the opposite. Okay, the circuit that we build will correspond to these actions. Okay, so again, let me write down the relationship. If I denote this V0 minus IIRM as the error of the current controlled voltage source, if it is greater than 0, then output voltage must be reduced, and If it is less than 0, the output voltage must be increased. Okay. And what does the transistor do? The transistor, if VGS is more than 0, then it pulls current from the drain and pushes current out of the source, right? If the incremental VGS around some operating point is more than 0, then there will be an incremental current flowing from drain to source. It's pulled from the drain terminal, so the drain voltage tends to reduce, and it's pushed into the source terminal, so the source voltage tends to increase. Okay. Now, similarly, if VGS is less than 0, the opposite happens. Now, if you compare these two, V0 minus IIRM, if this is more than 0, the output voltage must be reduced. So, the current must be pulled from the output node. And if VGS is more than 0, current will be pulled from the drain node. Okay. So, it looks like if you make V0 minus IIRM equal to the VGS, the incremental gate source voltage of the transistor, and if you look at what is happening at the drain terminal, what's happening is exactly what you want. Okay. So, from this you can infer that VGS must be equal to V0 minus IIRM, and the output is the drain terminal. Okay. Then it looks like the actions that we want to happen will happen. Okay. Now let's complete the circuit. We have an input current II, and we have the small signal equivalent of the transistor, GMVGS. Okay. This is the gate, this is the drain, this is the source, and like I said, we have to take the output at the drain or between drain and ground. So let me connect the source to ground and consider the drain as the output. Okay. If that's the case, then this VGS has to be equal to V0 minus IIRM. How do I produce this voltage? So let's say there is some node at which there is a voltage V0, and I have the current source which gives me II. Okay. So what is this saying? It is V0 minus II times Rm. To produce II times Rm, I have to make II flow through a resistor whose value is Rm. Then this voltage here in this polarity will be II times Rm. Okay. The circuit is not complete yet. So let's say I connect it to this node. You can see that the voltage here is V0 with respect to ground. So the voltage here will be V0 minus IIRM. So this will be V0 minus IIRM. Okay. So that's how we can get a voltage which is V0 minus IIRM, and we want to make it equal to VGS. Okay. So first what I do is exactly what I described here. I connect a resistor Rm like that, and II. So this voltage will be II times Rm, and the voltage at this node with respect to ground will be V0 minus II times Rm. Okay. And this voltage must be equal to VGS. The source is grounded. If I connect it like that, then VGS becomes equal to V0 minus II times Rm. Okay. So this is our strategy for building a current controlled voltage source. So what happens now? The gate source voltage equals V0 minus IIRM. If V0 minus IIRM is more than 0, VGS will be more than 0 and a current will be pulled from the drain node. And if you pull a current from a node, its voltage tends to reduce. This is exactly what you want to happen, because if V0 minus IIRM is more than 0, it means that the actual voltage is more than the desired voltage. Similarly, if this quantity is less than 0, then VGS is negative and this current will be pushed into the drain node, increasing the output voltage. Okay. So this is our current controlled voltage source using a MOS transistor. Okay.